You came back to learn more, and that's great. And what a great and exciting unit this is, okay? In this video, we are going to talk about digital images. How are pictures changed to binary? How does a computer understand pictures? And how is just binary changed back to images that we can see? Great questions. First of all, we have to just know the digital canvas is a map of bits. So of course, okay, any picture is changed to binary or is stored as binary inside the computer. Digital images are stored in computer system as bitmap images, which are a grid or map of tiny dots. Okay, so if you just zoom it in, you can just see the different dots of the picture. Each dot is called a pixel, short for picture element. Pixel, picture element, okay? Representing a single point of uniform color. So each pixel can have one color, okay? And because computers process binary, every pixel is assigned a unique binary specifying its exact color. So in showing pictures, we are changing different colors to binary, okay, and giving that binary of that color to different pixels. That is just how it works. So an entire picture is saved as a continuous stream of zeros and ones in memory. Okay, so a complete picture maybe just that is millions of zeros and ones in computer memory. And resolution is calculated as width multiplied by height. So number of pixels in the width and number of pixels in the height. Pixels per inch describes how densely those pixels are packed when displayed on a screen. Okay, so if our pixels per inch is just less or low, it means on 1 inch we have just gotten lesser number of pixels. But if it's high, it means in 1 inch we have gotten just a much more pixels, and just the pixels are dense there, so that results in a better quality image. Okay, and the impact of pixels per inch or just resolution is just a more clear and detailed image. Okay, and low resolution images lack data. When stretched to fit a screen, maybe just you will see a blocky or pixelated image like this. Okay, if the resolution of an image is small and you just stretch it to just make it larger, you may just see broken or pixelated colors. And what is color depth? Color depth is the number of bits used to store every pixel. Okay, for example, if you store the color of every pixel in 4 bits, so your color bit is 4. Okay, if you are just storing every pixel in 8 bits, your color depth is 8. Okay, and how many different colors can we just represent with that? We have gotten this simple formula, 2 to the power of n. See, if we have gotten just 1 pixel, we can just 2 to the power of 1, 2. So we can show only 2 pictures. Okay, for example, black and white. 2 bits, we can just store 4 different colors. Okay, 3 bits, we can just store 8 different colors. So we have gotten that one. Okay, so color depth is the exact number of bits used to represent or store 1 pixel. So color depth is calculated with 2 to the power of n, and for example 2 to the power of 1. If you have gotten 1 pixel, that is just 2 different colors. If you have gotten 2 bits for a pixel, so you can just show or store 4 different colors there. If you just use 3 bits for each pixel, so 2 to the power of 3 will be 8. So you can just show 8 different colors. And if you just you use 4 bits for each pixel, you can show 16 different colors. Okay, so that's very important. And the color depth evolution matrix, see here, this is a 1 pixel color depth, okay, or bit depth. Each pixel is shown with 1 bit. So you have either black or white. So you can just have a picture like that. 8-bit depth, 2 to the power of 8, 256 different colors. Okay, so classic retro games or things like that, they had 8 bits for each pixel. So you can have a picture like this. Okay, 256 different colors. And the 24-bit true color, which is just used by systems and by computers and cameras and printers right now, okay, that is 24 bits, which creates over 16.7 million different colors, okay. That is the reason that we have gotten photorealism, okay, because we have gotten just 8 bits for each color: red, green and blue. So 8 bits red, 8 bits green, 8 bits blue, that results in 24 bits per pixel. So I hope you have just understood how a picture is stored, okay? Number of pixels, that is resolution, width multiplied by height, and how many bits are you using to store each pixel, okay? And metadata, what is just metadata? Metadata is just very simple, okay? It's data about data. Look at this example. This yellow zeros and one, if they are just kind of the data of the image, okay, each one of them just kind of, for example, 8 of them or 24 of them showing 1 pixel on an image. We have just some other data as well on this image that simply tells us what is the width and height of this image, so we can just show the image very correctly, okay? Or how many bits from here should we just use for 1 pixel. For example, if it tells us that, yeah, the metadata can just tell us that, yeah, the color depth is 4, so we will just use the 4 first colors, then change it to a color, okay, and then 4 next to a. If it tells us that no, color depth is 8 bits, so we'll just separate 8 bits, okay, to show 1 pixel, okay. So metadata is data about data. Software cannot see the image. It only sees a massive string of binary. It relies on metadata. Metadata is simply data about data. It is additional, hidden information stored alongside the image file that provides the vital context needed to display the image correctly. Okay, so I hope you have just understood that. That is just information about the picture that gives different type of information. For example, it might tell you the author and copyright. It might tell you the day it was created. Maybe just it tells us the location, where was it created, the dimensions, okay, and color depth. And we just need to calculate the file size many times. Okay, you will have questions like this in your exam. They will just give you the width and height of an image and color depth of that and tell you that, yeah, calculate the file size for us, okay. So you have to know, to find out how much space an image will take on hard drive, you simply multiply the number of pixels by the number of bits used for each pixel. So width multiplied by height, that will just give us the total number of pixels, and each pixel, how many bits do they use, okay. So that is multiplied by color depth. It will give us the file size in bits. So see here, 1000 pixel wide, 800 pixels high, and the color depth is also 16-bit. So 1000 multiplied by 800 multiplied by 16 will just give us this beautiful number here, okay. So this formula gives us the file size in bits. But many times questions will tell us to give the file size in bytes or in KB bytes, in MB bytes, things like that, okay. So you have to understand this one as well. See, we have gotten bits, then 8 bits make 1 byte, 1024 bytes make 1 KB bytes, 1024 KB bytes make 1 maybe bytes, okay. So how can we just convert from bits to bytes and KB bytes or maybe bytes, okay. So that is very simple, a division, okay. Bits, if you have just got a number of bits, divided by 8, you will just get how many bytes are there. Then after that, if you have the bytes and you want to just get the KB bytes, you can just simply divide the bytes by 1024, you will just get how many KB bytes are there, okay. And the same, changing KB bytes to maybe bytes, you will again divide by 1024, okay. So raw bits are too small to be useful. For the exam, you must step up the unit, okay. So questions: calculate the file size of an image with width of 12 100 pixels and a height of 900 pixels and a color depth of 16 bits. Show your answers in KB bits. Pause the video, solve the question, and after that check the video to see if your answer is correct or not. Okay, good. I hope you have just solved the question. Now let's just check your answer. So we have gotten 1200 pixels in width and 900 pixels in the height and a color depth of 16. Okay, multiplying them together will just give us 7,280,000 bits. Okay, now the question has asked us to just give our answer in KB bits, so changing these bits to KB bits. So we will first of all divide it by 8 to just get the bytes. Okay, then after that we will divide the bytes to 1024 to get KB bytes. Doing this calculation, we will just simply get 33,750. Okay, so that is our final answer in KB bits. Clear? So the ultimate trade-off matrix. What happens if we want to have a higher quality image, and what happens if we want to just store or just save some space? So the golden rule of digital image, you cannot increase visual fidelity without paying the price in storage. So if you want better quality images, you will have to increase the resolution or color depth. Okay, so that will give you a better result or better quality, but that simply inflates the file size, that increases the file size. Okay, and if you want to send it over internet, it consumes your bandwidth. Okay, and also if you want to store it, it consumes your hard drive space. And if you want to just kind of decrease the file size, so lowering resolution or color depth, so that will save you some storage space, but yeah, that it sacrifices clarity, and it might just result in grainy or blocky visuals. Okay, so higher quality, higher amount of space, lower quality, lower amount of space. That's it. Wish you all the best. I hope you have learned. If there is any question, we will be just more than happy to answer you in the comment section. Do not forget to like and subscribe. Wish you all the best.